Good afternoon session. The first talk is by Tsang.
That's fine.
Facility.
Okay, so I'm very Tsang from Michigan State University. The facility for our new facility for rare isotope beams. And the charge to me to give the talk is on nuclear structure constraints on equation of state. Okay. But actually there are many constraints as I have shown you in here. So I cross out. Huh?
Oh, sorry, that's your computer.
No, there is still this meeting is being recorded. Oh, it's
Oh, you have to click up there then.
okay. It is so now.
Click on the slide so that it gets focused. Click anywhere. How about now?
Oh, okay. So there are many strings, so I cross out what the organizer told you to do. Okay, but you will see that there are actually, quite a bit of nuclear properties, which I will talk about some nuclear structure, just not only the nuclear structure constraint. Okay, so as you know, the one function or one goal of the equation state that we want to do is to connect nuclei to the cosmos. For example, in this case is a neutron star. So in here, this beautiful thing that I will show you, this curve is actually the result by our work. That hopefully at the end of the talk, I will convince you that we are able to do it by combining all the constraints I show in here. So this plot also show you the outline of my talk. I will first talk about all the constraints, not all, but selected few, so you get some ideas. Then I'll use the Bayesian, our group use the Bayesian inverse to combine all these strings to obtain equation of state as this one shown in here. That's for pure neutron matter. Okay. So yeah. Okay, so first let me talk about the neutron star constraint. Okay, that's just mainly for a higher energy. I move it down below 2, but I would say that for all practical purposes, as far as my experience is concerned, the neutron star constraint matters about 2 neutron star matter. But the other thing is this: a neutron star is different from neutron. The equation state for neutron star matter is different from nuclear matter. The reason is that neutron star has this unusual thing because its gravity is extremely high. Okay, so that's the equation of state has to obey this TOB equation. So as you can see, the TOB equation, in addition to energy density, you also have the mass and the radii. And so most of the time when you look at neutron star constraint, they come in the mass radii relationship, as you can see in here. So the example recently, we have quite at least 2 pulsar was measured by NICE, which is a X-ray observatory up on the International Space Station, and they measure 2 pulsar, one with 2 solar mass, the other one with 1.4 solar mass, and they measure the radius. And then the other thing that was very nice, and that was a lot of you have read about it, is the merger of the neutron star in 2017. So from the merger, when the neutron star getting close, they exert tidal force on each other, and so they deform. From the deformability, you can see the deformability here. You can see that the lambda is related to the R over M squared. The R over M, remember the R, the radii is the mass, is the equation state for neutron matter. Okay. Oh, so sorry. I think here. Okay, so these are the measurements that observation that we have got. The nicer result is here is mass versus radius, and then the tidal deformability is this point for 1.4 neutron mass. I think I've already just used these 2. Okay, so now we took care of this. Now I want to give you not just the range of the new constraint I show you, but actually where are all the constraints? According to density, not the pressure yet, just the density. You can see all the arrows. So And the other thing I want to say is that now we took care of the neutron star TOV equation, because neutron star observation normally give you measure just the pressure, not the microscopic origin of the neutrons of the equation of state. So from yesterday's lecture by Christian Dressler, you see that we can have the equation of state of nuclear matter can be distinguished for normally, you know, because for nuclear matter, we mainly consist of neutrons and protons. So then you can write the equation of state into two terms. One is the symmetric nuclear matter, where the number of density or number of neutrons and the number of protons or density of protons are equal. Then you have for any matter that has excess neutrons or protons, you need a second term. This is the S rho delta squared. That go with the asymmetry. The asymmetry is just basically a fraction of the excess neutrons or protons. Okay, and then this is this term. We call it symmetry energy, even though it's actually associated with the asymmetry of the system. Okay, so then you can see in here that I use the chiroeffective field theory that Christian have described yesterday, and then I separate it into the same thing. This is the pure neutron matter as a function of density, and here's the nucleus, symmetric nuclear matter and symmetry energy. Okay, so this is a calculation of initial calculation. Okay, so what do we do now? So the first thing is that let's take a look at the symmetric matter constraint. So remember that we have two terms in here. So the first one I would do is the symmetric matter constraint right here. Okay, so one thing is that you can write the symmetric density dependence of the symmetric matter in terms of Taylor expansion. So you have first the zero order, the E set and the K set, and then and expand it around the saturation density. Okay, so I actually spent 2 days trying to explain that, but I don't want to do it anymore. I throw away all my slides for that because Christian just taught. I don't think I can reproduce what he has done. Okay, he explained how he tried to get the rho zero and E set. And then after we did all the work is anyway, it's within error bar is plus is 0.16 for the rho zero and E set is minus 16 MeV. So I just leave it at that. And then there's a incompressibility is 230 plus or minus 30. For me, I use a larger range for 30 MeV. Okay. So that's the symmetric matter constraint at rho zero at the saturation density. But actually, there has been work in the past to trying to extract using hyper-ion collision to extract constraints beyond 1 rho zero. And as a matter of fact, as the DLL is the famous work by Danielowitz, Lacy, and Lynch in the Science article, where they use the heavy-ion collisions that have hyperpolarized and compressed. When they compress region, there is pressure. You will expect pressure. They can measure the pressure experimentally by looking at the flow. I think every one of you guys have already heard the last 2 days by measuring V1 and V2. Okay, so by measuring V1 and V2 and using PEBU simulation, they can extract what the pressure and the density. You know, so the density is in here. I think one is density, one is pressure. Okay. And then they extract the symmetric matter pressure versus density constraint in here. That's this one in here. Okay, so we'll come back to this. So now after, so I have the astro constraints and then the symmetric matter constraint. Now we go to symmetry energy constraint. That's where the nuclear structure and nuclear property plays a role. And you can see that there's a diverse constraints in here. It ranges from close to about 0.2 rho zero to about 1.5. Okay, and so well, you know, you can for those who are in the low energy community, you know that we've been working on it for the last 10, 15 years or last 20 years. So what have we done? So this is the most famous plot in here. There's a slope versus S, and Bauer had other representation. But anyway, the problem I have with this plot is this, you can see that there are many constraints that was plotted in here. Okay, is this that the reason that you plot S versus L is come from the Taylor expansion of the symmetry energy. Here. Can I get it here? I think, okay. And then you do the Taylor expansion, then you expand SL at S0, and then the L is a slope, K is a curvature. You can even go higher term for our Bayesian analysis. We go higher for the Q and the Z, okay, the third and fourth order. The problem that I have with just plotting it as S versus L is, for example, this HIC constraint in here. I know because that's our work. We know that in the heavy ion collision, when for low energy heavy ion collision, we collide just briefly and then it expands. So when it expands to lower density. So as a matter of fact, pretty much, if you don't believe my calculation, you can go to other calculation. Pretty much all calculations that expansion go to an expansion part of about 0.3 or lower. Okay, 1/3 or lower rho zero. Now you're talking about trying to describe this data, and then you extrapolate from 0.3 rho zero to rho zero. That's a large extrapolation. And I have to say that I'm guilty of it because I think we were one of the first ones who plot S versus L at that time. We didn't know better. Okay, so that the other thing that's very well known is this, that both masses and spin of nuclei are sensitive to 2/3 of rho zero, not rho zero. Okay, so pretty much anything that you're doing in here, this L versus S0 are extrapolation. Except for the calculation, everything, all experimental data are extrapolated from other density. Okay, so that is worse. I mean, recently there's this article by Jerome. The article is very good, but I found this plot quite, I don't know, amusing or distracting or confusing. Okay, so then the question is, how can we move on from going to here? Okay, what's noticed by Bill Lynch was this, that there are different slopes depending on different experiments. Okay, then I'll describe what I call a crossover. So if you extract out 3 different type slopes in here, 3 different type of measurements. So these are mainly mass. So mass measurement by Brown and DFT, the density functional theory, and also the isobaric analog states. Okay, you can see the slope are similar. Okay, so the crossover method is, I just do it this very quick. It's Alex Brown first used the Sturm interaction that fit all the properties of this. Okay, so from these properties, then if he has a Sturm, so he can extract his A, B, C, and D. Then he plot them. But if all he did is, if he still required that, he changed the skin. So any Sturm interaction give you the less skin. Now, if he changed the skin number, then if we fit the parameters, then you can do this. Okay, so he has in here, he has three things in here. So this is the skin with 0.24 Fermi. This is 0.2 and 0.16. You see that they obviously they have different slope because the skin is related to slope, and also because slope and S are correlated. So there's also different S values. And so what you do is that you look at his S and L value, as you plot it in here, you see that they lie along one line. So it means that anytime you can change your skin, as long as you fit it along this line, you will have a Sturm interaction that fits the nuclei that I described, and as well as any other. But the main observation is that they all cross over. and they cross over around 2/3 of the density. That's the point that we want to say. Oh, okay, so here. Okay, sorry. Okay, so the crossover, so then from the crossover, you can extract the density versus the density as well as the rho. Okay, you can use this not only on this one, but for the other 3 masses, then you can see that you got a result very, very consistent with each other. Okay. And then we use this for other observations too. Sorry, there's a time lapse between here and there. Okay, anyway, so then we can use the same crossover technique. I don't want to go into detail. If you want to look at it, you can see this reference. And then we can look at the heavy ion collision. And then now, so we get a range of the density, not a large range, but from 0.2 to around 0.67. Okay. So then the obvious thing is this, that actually I only did that just a couple of days ago. I was quite surprised. So then was it we got that. Well, how consistent is it with the chiral-effective field theory? Okay. So this is what I plot. And I thought that was really nice. I think I thought it a few years back. At that time, the chiral-effective theory was not as nice as this one. So that was pretty impressive. Then the question now is, okay, now you solve. I finished the charge by the organizer. I'm done with the nuclear structure constraint. Okay. So, but the interesting should be about rho zero. Okay. So what's happening with rho zero? So in order to make rho zero, we learned quite a bit from doing the low density part. Okay. So we know that the high energy part is actually difficult to measure. The reason is that you want to go high density, you have to increase the energy of the beam. If you increase the energy of the beam, the reaction you're talking about is no longer low temperature. High temperature diminish the isospin effect or the symmetry effect. Okay, so what we decided to do was inspired by some publication by Bao, is to measure pion. Pi emitted at the early stage of the collision reflect the high density environment. We look at the pi minus 5 plus ratio, which should be proportional to the NP, which is basically the symmetry energy effect. However, the effect we know is small. It's less than 10%. I say about 10%. It's actually much less than 10%. And then the other thing that we found out was this, that we don't just measure the pion energy, but we have to measure the spectral. And then we look at the spectral ratio, as I will show you that more recent transport models show that it's the high energy pions that are sensitive to symmetry energy. And so the other thing that we learned from the low density experiment is that we want to expand the range of the system. So we use radioactive beam to increase the delta, the asymmetry range. Okay. So what we did then, we said that's 10 years ago, maybe 12 years ago. So we decided to build a time projection chamber. And that time projection chamber, as you can see in here, measure pions, pions in here, as well as other particles. And we took that to Riken because we need we want to use radioactive beam on tin 132 and as well as tin 108. I remember when Bao did the calculation of 132 and 124, I said, that's crazy. You'll never get 132 beam. I was wrong. So this is during the experiment, that's what we see, online, that we see stuff. I don't want to dwell on that too much. So we got the data, we plot the ratio, pi minus 5 plus ratio. This is for one system, 132 and 124. And as a function of PT, as you can see that you can see from the DCQMD by Dan Postma, you see that the low density part is not that sensitive to the different, see here I show the 4 different calculations with 2 different L and 2 different effective mass. It turned out that the pi ratio is not only just sensitive to L, but also sensitive to effective mass. So we are not able to, so the L or the S0 value that we obtain is rather large. Okay, you can see it here. Okay, so but we did get this data. So then now you see what you get if you plot the chiral effective field theory, then you will see that I think it's not as surprising, right? Chiral effective field theory normally is more softer than most experiment, especially at high density where they can extract, I mean, they can give you the quantity, the uncertainty principle, but it's still just softer than the data. Okay.
So is this pi plus or pi minus?
Pi minus pi plus, pi minus over pi plus is a single ratio.
Okay, on the right, the PT dependence is what's the reason for the PT dependence?
The PT dependence, you just have pi plus pi minus pi plus actually. Okay, so in here you have in here actually this is just a Coulomb. Okay, because pi minus and pi plus have different Coulomb, so you expect at the low PT value you will have this increase, and then we try to do the double ratio, and the double ratio experimentally does not cancel all the Coulomb effect, but for the transport model it does. Yes, Bill.
I just make a comment here that this is sensitive to the assumption of the delta mass. So once you consider that sensitivity, the only place where you really pin down the symmetry energy is about 200 MeV OSC.
Yeah. So here is from the transport model calculation, we know that this is not that sensitive to the other parameters in it. So I want to show out is that this analysis is mainly done by postdocs and especially students, including Tommy, that you will hear about him later. Okay. So I show you not all the constraints, but enough in each category that I want to just list them all. These are all the constraints that we will be using to use to do the equation of state extraction. So I want to say that this work is mainly done by Tommy. I mean, in collaboration. Tommy is actually is part of his thesis work, and also Rohit Kumar is a postdoc in the lab, and also Bill. So
question: are you just using the error bars for the mass and the radius and penalty component, or are you using the full posteriors?
So here the error bar, we actually use what they gave us, Riley and Mueller, the published.
Right, but the posteriors are not symmetric. So like
No, this is not a posterior. Yeah, I'm just listing just the constraint.
No, I'm just asking in your analysis, do you use the posterior or the error bars?
I use the error bars.
Oh.
Okay, I use the error bar, and as a matter of fact, as you know, the data is analyzed by two groups, Riley and Mueller. So we give each one a weight of 0.5 so that we don't double count. I mean, they are not two different events. Okay, and then so then we also have this the probability value is also in. So what we do then, so this is just a graphic representation of all the constraints that I have listed, and then you can see in here and then now let me show you. So this is Bayesian. So what we did is we put in the constraint, put in a Bayesian analysis, the equation state, we parameterize the equation state so that we can create a prior that cover most of the constraint, and then we put in a neutron star model. And then we extract the equation of state parameters and the posterior with the uncertainty. So before that, for the Bayesian analysis, we only use the constraint and the error bar associated with it. Okay, so this dotted line in here that corresponds to the priors, 95%. So you can see that as I said, our philosophy is we put our prior the parameter of the equation of state so that the prior will cover most of the as much as possible all the error, all the data. Okay. So now, then from the Bayesian inference, we can get the posterior. So these are the posterior, the dark color, the dark green the contour is the 68%, and then the light green, the light blue one is the 95%, and then The other one, the blue line, is just the prior. So you can see that we obtain the equation state for symmetry pressure versus density, density dependent symmetry pressure, density dependence of the symmetry energy, as well as the RM relation of correlations, and also the pressure of the symmetric matter density pressure. Okay, so now the next question is that I don't want to go into the other details, so let me just go on. So then what about, yes?
4 minutes.
Okay, so what about the background of, for the highly effective field theory? So remember the highly effective field theory, give me all the composition of the equation state. So I can just compare that. So on a whole, especially below row 0, there is I would say they're broad consistent with the highly effective field theory. But beyond that, at a higher density, then they started to deviate. Okay. So here is the neutron star, because we have a neutron star model, so we can also compare the neutron star equation state, that's pressure versus density, and then compare to other literature values. So this is the Who's et al. By in the science, and so the main difference between theirs and ours is this: that at the low density they use highly effective field theory, so that's why at the low density part they're lower than ours. But in our case we just use experiment, we didn't use any ab initio theory, and the broad band is from just only using astrophysics. Okay, then you can see our and as well as Who's have a narrower range of the equation state. Okay. So let me just go through this very quickly. So I already showed you that the heavy ion collisions has especially at the 1.5 row 0, a very large error. And that's coming from the fact that all heavy ion collisions, the data has to depend on transform model in order to extract the equation state. Okay, and that we know that there's some problem with the transform model, and so that's why we have formed this transform model evaluation project, where we in the beginning we took 20 codes. Actually, we got the collaboration of 20 codes authors, and then we found that the different codes use different approaches, different approximation. However, the agreement is actually pretty good if it's in a control box study. Then when we put them into the actual, to do the actual data, to do the actual collisions, then there are differences. And so the first things that we think we need is for the transform model is to need quantification of uncertainties. And without that, and so there is a discussion of all these problems in the white paper by Aneska Sorensen, and she said that she welcomed all suggestions and comments. And she also said that you can become an endorsing author by going there with the paper and write and to send to her that you want to be an author. Okay. Okay, so finally I want to conclude. Okay, so I believe that we will have a comprehensive co-equation state. Not just the L or S0 or K0. So, and in the past decade, the amazing thing, and I would say, is the discovery of the neutron star merger and also the data from the night. Okay, astrophysics, and also we have advanced quite a bit now too, mainly because of Bayesian analysis to connect experimental constraint for symmetric matter and symmetric matter to the neutron star. In the near futures, I would say that I think everybody will agree there will be new neutron star measurements, and there will be updates of the symmetric matter constraint. The one that I show you was since 2002, and then we'll have with the new results from HADAS and the beam energy scan from Rick. Then we expect there will be improvement of symmetry energy constraint that where we have a lack of data is between 1 to 3 row 0 for symmetry energy. Okay, but I believe the largest breakthrough will come in if we have it, if we're lucky, it's the transform model simulation. We're basically right now we're limited by that. Because of that, I would advertise that in our field, there will be a new facility every 400. We will have new experiments and new theory to explore this golden window or golden era of the neutron star physics with heavy ion collision. So for all the young people, come here. This is where the future is. Thank you very much.
Yeah.
So I really appreciate the discussion on the symmetry, energy versus density. That helped explain a number of things. I do have a question though, is why do we know that the Taylor expansion is the best way to do this series? So like from lattice QCD, when we talk about critical points and phase transitions, we expect that the Taylor series is not going to work all the way out. And we do things, you could do like a Pade approximation, or you could do other approaches. And in neutron stars, you could certainly have phase transitions and other things as well. So have people explored other types of series expansions?
We haven't, and as a matter of fact, I will actually point out to the fact that the way that we did our methodology. So you can see that the equation state C is in here. You can change the equation state. We just use a parameterized equation state, mainly actually with actually ours is not it's sort of Taylor expansion, but actually it's a meta modeling. Okay, to remove the correlations between the different coefficients. And then the same thing, the neutron star model, we believe that it will, you see that we only plot to 3 rho 0, because we believe that we need improvement in the neutron star model also. So as what I'm saying is I want to emphasize that the fact that the method that I'm telling you is you can change many ingredients in here. Constraint, you have new constraint, put it in. You don't like certain constraint, take it out. And then the same thing for, you can use different equation state. We have not tried yet. And then you can also improve your neutron star. But that can be.
So for the 3 times density, what are the corresponding beam energies we?
So I would say that so probably around 600 to, oh, actually more than that. It's around 1. So for the, so there are 2 things. For the symmetry energy, I think that is very hopeless. But to go for the symmetric matter, to go to 3 rho 0, you probably go about 1 GeV. So as a matter of fact, the symmetry energy from Daniela West, what he showed, let me see if I can get it. Oh.
I guess you really want to compress it, but you don't want to heat it up, right?
Yes. Well, you cannot avoid heating it up. So what you need to do is in your transfer model, you have to extrapolate down to T rho 0. So you can see in here that I believe the energy range that he was using, but maybe you can confirm, is between 1 to 10 GeV. And so he can go up to 415.
I think, so, you know, you can of course make extrapolations further. The question is, how well do you believe your extrapolations? Then it was an analysis that was just provided in the SWOOP article of the GSI data. And they were going up to something over a GeV, and then they were extrapolating up to 3 rho 0. That may be about as ambitious as you could be. So you do need a fair amount of energy to get to 4 rho 0, but I mean the beam energy scanning is definitely covering that. So,
Yeah.
So I think the problem here is, and if you look at the science article, you find out that there was a discrete difference between the best fit for the transverse flow
V1 and
and
V2.
the V1 and the V2, and I think. Well, let's see, the beam energy scan will give a whole new set of data. And then maybe that discrepancy will be resolved. If that's true, then I think the uncertainty in the up to 3 rho 0 will get narrower. The 0 value will get narrower. So really look forward to seeing that.
For the beam energy scan, what you mean is our fixed target.
Yeah, exactly.
Yeah,
That's what I didn't call that today. That's what I got that from you guys. So.
Okay, so let's take a question from the Zoom. Zidu.
Yeah. Okay. Yeah. Thank you so much. So, hello, Betty. I have a very general question for you. So in principle, for the neutron star physics, we are interested in the zero temperature equation state. I'm just wondering what's the model and what's the assumption that we need to make to constrain a zero temperature symmetric nuclear matter equation state by using your heavy ion collision data.
So this is what I'm saying is that that's highly dependent. We are highly dependent on the transport model people. The transport model will have to simulate our data, and that has to extrapolate to the zero temperature. And according to Pavel, he said that he can do it.
Well, so what, I mean, if you have a transport model, like a BUU or QMD, transport is certainly reasonable over this energy regime. You're not really in the quark dominated domain. Then you could parameterize your basically your potential energy. And you parameterize the energy stored for zero temperature matter. And finite temperature matter, it comes to the kinetic energies of the nucleons and the produced particles. And then you ask at the end, you describe the data with transport theory, and then you ask, what is the corresponding pressure associated with that equation state that you put in, which is a zero temperature equation state? What is the pressure for that when you're at zero temperature? The other pressure that you're getting in a collision will be coming from the kinetic motions of particles.
Is this extrapolation have some large model dependence? Or?
Well, it's done by two independent groups, and I think if you take into account the input values, I mean, the GSI people use different data than Powell's. I think that they're basically the same.
Yeah. So it's
so I mean, you have to ask. You need to come up with an argument why there's some other form of pressure besides the pressure coming from the V field in these calculations, and the pressure is coming from the kinetic motions of the particles. If that's true, then this approach would need to take that into account. So
let's answer the other question.
Okay. Yeah. So Agnieszka.
Yeah, hi. I just have a couple of comments. So first, the question was what beam energy that would this counter corresponds that would be approximately from like 2.4 square root of S to around 6. So it's both hardest and fixed target beam energy scan. Second of all, this contour has been obtained with a parametrization of the equation of state, which is based on a Taylor expansion, which I think is not the best approach, as already Betty has suggested. It's not the best approach for symmetry energy. It also is not the best approach for symmetric equation of state. But I think doubling down on what Bill has said, the fact that this contour is so not really that much constricting is because the EA95 data is not self-consistent. So last year we did analysis together with Dima Olenichenko, a Bayesian analysis of this data, and you cannot describe V1 and V2 simultaneously, no matter what you do. But you can describe the star data. So
but that was already discussed in the Science article. That point you make, that they were not, they were.
I mean, yeah, sure, yes. I just want to, we confirmed that they were not. Because our equation of state was more flexible, right? Our equation of state was not a Taylor expansion, but it could be independently varied in different density regions. So the question was, well, if you use such a more flexible equation of state, can you perhaps describe this data better? And the answer is no. You really can't, no matter what you do. So that's my comment.
Thank you. I have a question about this pion ratio, the PD spectrum. Just want to understand some basics. So, but you said that the enhancement low PD in the ratio is due to Coulomb. But if I talk about the total pion field, does it still matter if you look.
The
at
total you ratio,
Yeah,
actually, we were sort of surprised. We look at the total pi and u, and they turn out to be very similar, the ratio, very similar to the higher, so sorry about this. Okay, here's the data. Okay, okay.
yes,
It turned out to be the ratio is about about 2 point something, but anyway, a power law to describe the ratio, because remember that we have 4 systems. Okay, so we actually have an N over Z dependence. So it's higher, the time ratio is higher than what you can see in the N over Z squared. That's but
so it's not
So-
only, it's higher than what you expect from us in.
no, it's higher than what you expect from the simple N over Z ratio because of the production of pi.
Right,
So, okay, so actually to me, that's the interesting thing, right? Because it's higher. So, but transfer model cannot explain that. That's the problem. So then when we look at that, we also look at the ratios as a function of PT. They don't change that much. That's the supply chain.
So what is in this model, that?
The DCQMD,
Yeah, I have no idea this model, but it have Coulomb unit, so it's
Oh, yeah.
UGP and then, but you mentioned, you have a comment saying that most of complaints are coming from high PT region.
so
the
it's here. I cannot see, so you can see, I disconnect the thing, so you have to do it in here. So you see that these are the 4 calculations on different L and delta M and P. You see that they are very close to the same here.
Okay.
Okay, but the high PT, you see that they separate out. And so that's why we think that this is the region. And as a matter of fact, if you look at the paper in here, that's the region that will extract the L versus.
I see.
delta.
I think, actually, can you show the full pi inspector? You had that in,
I'm not so sure, do I have that?
you were showing it earlier. Maybe it was the first slide.
Thank you. This one?
Yeah, so if you look carefully at the green, so this is a log plot, the other one's, Scott, if you look carefully, there is some difficulty in describing the very shape at the peak of the pi and spectrum. And that's a problem in both pi plus and pi minus, and it shows also up in the ratio. And the transport theorist, Van Kozma, was concerned that his lack of description of non-resident pi production was responsible for the problem he's seeing at low PT. So he just concentrated in on the high PT. Actually, it's interesting because if you do actually do a ratio, a double ratio of the pi plus over pi minus or pi plus, but then you have 2 systems. The data, the theory was almost exactly one thing. So there is some shape issue at the low part of the PT spectrum, and he may be right that there's some non-resident effect. But then that's why we focus at the high part of the PT spectrum.
Okay. Thank you.
So you should talk to Tommy if you are interested. He has all the data.
Tommy is a good guy.
Yeah, he should give this talk, but he has to work on his project.
Okay.
So postdoc cannot do whatever they want.
So let's thank that. So our next speaker.